lecture of the Fourier transformation. Today I will solve integral equations with the help of the Fourier transformation, and then I will discuss the convolution theorem, Parseval identity related to the Fourier transformation, and then if time persists we will solve the partial differential equations with the help of the Fourier transformation. So let us solve the integral 0 to infinity, say fx into cos sx dx. Let us solve this integral and suppose that its value is 1 minus s when your s is between 0 to 1, and say this is your 0 when your s is greater than 1. So let us solve this integral. Solution. Here you can see that this is the definition of the Fourier cosine transformation. So that means this left hand side is, so this means the left hand side is your Fourier cosine transformation, and this is equal to 0 to infinity, and it has value, and its value is this integral. Now we have to find out your fx. We have to find out fx. To solve means here your unknown is fx. So now the fx means for fx we will use the inverse Fourier transformation. So the inverse Fourier transformation is 2 upon pi, and then we will have the Fourier cosine transformation, and as we are using the inverse cosine transformation, so we will have cos sx and then integration with respect to s. Now here you can see that as we are integrating with respect to s, now when your s is between 0 to 1, we have the value of this FCS as 1 minus s. So only when your s lies between 0 to 1, we are getting the non-zero value, and for the rest cases the value is 0. So we will write 0 to 1, and the value of this FCS is 1 minus cos, and then cos sx ds. Now use the Bernoulli rule of integration. So we will get 1 minus s. Integration of cos s will be your sin sx upon s. Then we will have minus sign. Then the differences, now this will be your minus, so this will be your plus. And integration of sine will be minus cos sx divided by s square, and the limits from 0 to 1. Now you can see that at this first term is 0 for the upper limit as well as for the lower limit, because at s equal to 0 this is your x, not s, because we are integrating with respect to x, we are integrating with respect to s. So here you can see that at s equal to 1 this is your 0, and at s equal to 0 this is again 0. So we have only this term. So your answer is, therefore fx will be 2 upon pi. Then here your upper limit will be, when your s is 1, this is your cos sx. So if your s equal to 1, then we will get minus cos x upon x square, and if your lower limit, if your s is 0, then we will get plus 1 upon x square. So your answer will be 2 upon pi x square 1 minus cos x. So this is the solution of the integral equation. Let us solve one more question. Solve integral 0 to infinity fx cos sx dx equal to e to the power minus x, e to the power minus s. Again, this is the definition of your Fourier cosine transformation. So using the inverse cosine transformation, your fx will be 2 upon pi 0 to infinity. Then we will have the formula of Fourier cosine transformation. Then cos, as we have cos, so we are writing here cos sx, and then integration with respect to s. So here you can see that the value of FCS is equal to e to the power minus s, so we will get e to the power minus s into cos sx into ds. Now we can integrate this term. So integration of this will be, now integration of this term is equal to 2 upon pi. Then in the bracket we will have e to the power minus s upon 1 plus x square, and then minus cos sx. Then we will have minus sign, and then the differences of this will be a minus, so this will be plus x into sine sx, and then the limits from 0 to infinity. Now again, if your s is infinity, then we will have e to the power minus infinity, so it is 0. Now if your s is 0, then this will be 1, so we will get 2 upon pi 1 plus x square. So this is the solution of this particular integral equation. Now if you use, okay, so this is your solution. Then let us solve one more question. Solve the integral, or you can say that evaluate the value of the integral cos sx upon 1 plus s square ds. You can say, let us prove it, not solve. Let us prove that the value of this integral is equal to pi by 2 e to the power minus x for x greater than or equal to 0. Let us prove that this is equal to e to the power minus x. Solution. We have two choices. Either you can take fx equal to e to the power minus x and then take its Fourier cosine transformation, as we are getting cos sx. So for the first method, take fx equal to e to the power minus x and then take its Fourier transformation, Fourier cosine transformation, and then you will get the answer. And as I am solving the integral equations, so let us find out the value of this integral e to the power minus x cos sx dx. Let us consider this integral equation. Now the value of this integral is equal to e to the power minus x upon 1 plus your s square. Then we will have minus sign, and here we will get the minus cos sx. Then we will have differentiation, and we will get minus plus, so we will get s into sine sx, and then the limits from 0 to infinity. So again you can see that our answer will be 1 upon 1 plus s square. So that means the value of this integral is equal to 1 upon 1 plus s square. Now let us take its inverse transformation. Here I have given the value of the Fourier cosine integral. Now let us take its inverse. So inverse cosine transform of fx equal to e to the power minus x is your fx equal to 2 upon pi, then 0 to infinity. Now FCS, that means its Fourier cosine transformation. Here we have taken the Fourier cosine transformation of e to the power minus x. So this will be your cos sx, and then the integration with respect to s. So this is equal to 2 upon pi 0 to infinity. Now the value of FCS is equal to 1 upon 1 plus s square, then cos sx ds. So you can see that here the integral 0 to infinity cos sx upon 1 plus s square ds is equal to pi upon 2 into fx. As our fx was e to the power minus x, so this is your pi by 2 e to the power minus x. So this is your answer. So we have solved 3 questions related to the integral equations. Now let us prove the convolution theorem. So convolution, the convolution product of two functions ft and gt is defined as the convolution product of ft into gt is defined as integral minus infinity to infinity fu gt minus u du. This is your convolution product. And convolution theorem. Now, convolution theorem says that if your Fourier transformation of ft is fs, that means if the function ft is piecewise continuous and integrable, similarly if the function gt is piecewise continuous and integrable in the interval minus infinity to infinity, then the Fourier transformation of this convolution product is equal to fs into gs. That means the Fourier transformation of ft into the Fourier transformation of gt. Let us prove it. Now the Fourier transformation of this integral is equal to, let us use our definition. This will be equal to minus infinity to infinity into ft. That means ft means this function, minus infinity to infinity into the function into e to power ist, then e to power ist into dt. So this is the definition of the Fourier transformation of some function. Fourier transformation of some function is equal to minus infinity to infinity into that function into e to power ist into dt. As you can see that the limits are constant, so we can use the change of order of integration. Now let us change their order. Let us change the order of integration. As the limits are constant, so there will be no change in the limits. So we can easily change their order. So this will be your fu gt minus u and dt, and then we will have, say this is your, and at outside we will have e to power ist into d using change of order of integration. So let us assume t minus u equal to v. So you can see that your dt will be dv, and there is no change in the limits, because if t equal to infinity, we will have v as infinity. If t is minus infinity, we will have v as minus infinity. Therefore, the Fourier transformation of 0 to the left hand side, that means your ft star into gt, is equal to, now here you can see that this is your minus infinity to infinity fu into gt minus u. Now t minus u will be your v. So this is your gv. Now in place of dt we will have dv, and e for ist. Now in place of t we will have u plus v, and then du, and then dt is your dv. So this will be du. Now we can break it as minus infinity to infinity. Then we will have minus infinity to infinity fu. From here we will get e for isu, then du, and at the outside we will have gv into e for isv dv. So, or you can say that here we will get gv, let us rewrite it. Here you can see that we will have gv into e to power isv and then dv, and at outside we will have your fu into e to power isu and then du. Now what is this? This is your definition of the Fourier transformation of gt. If you write v, if you replace our variable v by t, then this is your minus infinity to infinity gt e to power ist dt, which is your Fourier transformation of gt. So this is your gs. So this is your gs, and in the bracket we have e to power isu du. Now this is your ft e to power ist dt. So this is your Fourier transformation of fs. This is your minus infinity to infinity e to power ist ft dt, means the Fourier transformation of ft, which is your fs. Thus Fourier transformation of ft star into gt is equal to fs into gs. So this is our convolution theorem. Next, we have the Parseval identity. Again, let ft and gt are two functions, or actually assume let Fourier transformation of ft equal to fs and the Fourier transformation of gt equal to gs. That means, again, if their Fourier transformation exists, that means the functions are piecewise continuous and integrable. Then first 1 upon 2 pi minus infinity to infinity fs into gs bar ds is equal to minus infinity to infinity ft gt conjugate and then integration with respect to t. So this is the first property of the Parseval. This is your first identity. And for the second case, if your ft equal to gt, then here we will get fs modulus of fs square, and here we will get modulus of ft square. So this is your Parseval identity. Let us put the first part, and second part is very easy. We have to replace our gt by ft or ft. That means my gt will be the inverse Fourier transformation of a function is defined as 1 upon 2 pi. Then we will have minus infinity to infinity. Then the Fourier transformation of gt says this is your gs, and then we will have e to the power minus is x, and then the integration with respect to s. So this is the definition of gt, and the gt conjugate will be 1 upon 2 pi minus infinity to infinity gs bar, and then we will have minus minus plus ist ds. Now let us take this right hand side. So this right hand side is equal to, right hand side means minus infinity to infinity ft gt bar. So this right hand side is equal to so now this is equal to 1 upon 2 pi minus infinity to infinity. So this is equal to, now this is your ft, and the value of gt bar is 1 upon 2 pi, and then we will have integral minus infinity to infinity gs bar, and then e to the power ist and ds. Then at outside we have dt. So this is our this integral. Now again let us change the order of integration. Now on changing the order of integration, let us take this t inside. We will get minus infinity to infinity minus infinity to infinity ft e to the power ist dt, and at outside we will have gs bar into ds by change of order. Here we can apply change of order of integration, and there will be no change in the limits because limits are constant. So now you can see that this is the definition of Fourier transformation of ft. So this is equal to minus infinity to infinity. Now this is your definition of the Fourier transformation of some function ft, which is your fs. So this is your answer. That means this was your left hand side. So if, yes, this was the left hand side. So minus infinity to infinity ft gt bar dt is equal to this term. Now if ft equal to gt, or you can say that if gt equal to ft, then we will get the second result. That means minus infinity to infinity modulus of ft square. Now this will be your a into a conjugate. That means mod a square is equal to, now here again we will get a into a conjugate. That means modulus a square. So this will be 1 upon 2 pi minus infinity to infinity then modulus of fs whole square ds. So this is the second Parseval identity. Now let us solve a question related to this Parseval identity. So question, find the Fourier transformation of fx equal to, or you can say ft equal to 1 when your mod t is less than equal to a, and this is 0 when your mod t is greater than 0. So if this is your function, so when your mod t is greater than a, and evaluate and reduce integral 0 to infinity sin square ax upon x square dx, and reduce the value of this integral. Solution. First of all, let us find out the Fourier transformation of this ft. Here our ft is equal to 1, and I have already told you what is the meaning of mod t less than equal to a. Mod t less than equal to a means if mod t equal to plus t, then we will get t less than a. Now if mod t equal to minus t, then we will have minus t less than a, and if you multiply minus sign on both sides, then this will be a plus t, and now this less than will become greater than, and we will get minus a. So that means our t is greater than minus a and less than plus a, and for the second case it is 0 whenever it is greater than a. So that means our ft is 1 for t between minus a to plus a. Therefore the Fourier transformation of ft is equal to fs, and the formula is equal to minus infinity to infinity ft e to power ist dt. This is the formula for Fourier transformation. Now here you can see that only when t lies between minus a to a, the value of the function is non-zero. So we will break it only for minus a to a, and for the remaining cases the value of the function is 0. So this, now here the value of the function will be 1, and we will get e to power ist dt. Now its integration will be, the integration of e to power ist will be 1 upon is, then integration ist, and the limit from minus a to a. So this is equal to 1 upon is, then we will have e to power isa minus e to power minus isa. Now this is equal to, now e to power I theta minus e to power minus I theta equal to 2i sin theta. So this is equal to 2i sin theta, that means sin as divided by I into s. So that means this is your 2 sin as upon s. So this is the Fourier transformation of this function ft. Now we have to find out the value of its square, the value of the integral of its square. So let us use the Parseval identity. Using Parseval identity, and this was 1 upon 2 pi minus infinity to infinity modulus ft square dt is equal to minus infinity to infinity. I think our Parseval identity was 1 upon 2 pi. Here we have fs square, and in the right hand side we have mod ft square. Now for fs we have this integral, so this is equal to 1 upon 2 pi minus infinity to infinity. Now fs means this Fourier transformation, and its whole square will be your 4 sin square as upon s square ds. And in the right hand side, you know that the value of the function ft was 1 for t between minus a to a, and 0 for remaining cases. This was the value of the function. So for minus a to a, the value of the function is 1, so this will be 1. Now the integration of 1 will be t, so the answer will be your 2a. Integration of 1 will be t, and for the limit we will get a, and for the lower limit we will get minus a. So this will become plus 2a. Thus 1 upon 2 pi integral minus infinity to infinity sine square as upon x square ds is equal to 2a. So that means integral minus infinity to infinity sine square as upon s square ds will be, now this is your, you can say that now this 4, this 2 will be, this 2 and 2 will be 4, so this 4 will cancel. So we will have just a into pi. Now as you can see that this bracket is even function. Sine square is even function, s square is even function. So we can write it 2 times 0 to infinity sine square is upon s square ds, and this is equal to a pi. Now if a equal to 1, then integral 0 to infinity sine square s upon s square ds equal to pi by 2, and this was the answer. And if we in definite integral we can replace the, we can change the variable. Now if we change the variable, then our answer was sine square x upon x square dx is equal to pi by 2. This is your answer.